to divide the discussion in two. First, I want to show a bit more of how squeezed light is useful for improved sensitivity. And I'll do several calculations about that. And then I want to talk about entanglement, actually, and to also clarify the relation between entanglement and squeezing. In a way, they are two sides of the same thing, but they seem extremely different. So we will discuss a little bit of that, and in that context we'll discuss time energy entanglement and also polarization entanglement, because those are common examples. I mean, we can talk about entanglement in practically any degree of freedom, but those are two interesting examples, one of a discrete set of levels, another of a continuous case. So one would be a continuous entanglement, the other one would be the other one would be discrete. So as I said, targets. One, squeezing and two, I want to talk about and we're going to try to talk about time energy, and okay, so So here, so we start with number 1, and we have here 2 things that we want to do, and that is SU11 and SU2. So I think I mentioned that several times. So we are. I want to first do a quick calculation on how okay. Oh. I come here tired, but never mind. So we want to talk about or the what I would like to do is like consider basically homodyne of squeezed vacuum. Now, in a way, what do I mean? I'm saying something like, okay, this is a 50-50 beam splitter. I have here state alpha, with the alpha being large. I have here squeezed vacuum. And I want to measure the intensity difference. Now, why is that related to squeezing as a resource for interferometric sensing? Because, so this is what we're going to calculate. So we're going to calculate this, and we're going to calculate the measurement, we can measurement noise. Now, why? Oops. Why is that important? Well, the point is, if you remember, when we think about, for example, a Mach-Zehnder interferometer, then what do we have? We usually have here some input state, and then here there's a phase that we would like to measure. And eventually here we have, well, we don't necessarily need to do exactly that to take the difference. Now, the point is that, and here there's another, what we're doing now is we're thinking about introducing here something that we usually introduce vacuum, and now we're going to introduce squeezed vacuum. Why? Because this entire thing, maybe better to use a different color. Shalom, shalom. Shalom. As I showed you last time, this whole thing can be seen as a black box with 2 inputs and 2 outputs, and this is equivalent to a beam splitter of reflection equals cosine phi and transmission equals sine phi. Now, and specifically, we're interested in the case. So, well, we know what those intensities are. So, again, this is a reminder. Like if this is, say, I1 and this is I2, and I don't know, those are the intensities, but so I1 goes like cosine squared phi. This is I1, goes like n, where n is the input intensity, or this one is I2. And where, and here at this is pi over 4. That's where the intensities are equal. Here, this looks like a good place to look at, because here, this is what we already know. This is the average number. So that is the average number of photons. Let's say N1. Average number of photons is a function of phi. And so here, at this point, like near phi equals pi over 4, we have, so, or if I think here phi equals pi over 4, so we think of, say, of phi equals pi over 4 plus delta phi. So this is a small change. Now, what do we see? We see here that one of the intensities goes up, the other one goes down. So if I take the difference, it's a good idea, because the difference will show me sensitivity. So near here, delta n is a function of delta phi, or delta n average. Let's do it like that. Delta n average is a function of delta phi, is simply n times delta phi. That's because they're linear. And you can, of course, check me. So, like, because in a way, n2 minus n1 of phi equals n overall times cosine squared minus sine squared, and this is n times cosine of 2 phi, and well, that's it about. And indeed, near pi over 4, this is where this cosine will be 0. And so if I think about that, if that's, so if we measure, so here I should be saying that, let's call that delta n of phi. That's what it is. And here I'll say on average. Here there's an average. So now, so basically here, the question is, this is what I measure, and I want to get out phi. So I'm saying something like, okay, so I am near here, So in that vicinity, near, so if phi equals pi over 4 plus delta phi, near this vicinity, we will have, so I may say that this is approximately n times delta phi. Now, am I accurate? Maybe there's a factor of 2, but I think that here I missed another factor of 2. So I think that it should have been here this, or and well, so yeah, the definition of phi is open for discussion. So let's be here. Yeah, well. Okay, let's keep it as it is. So 2n twice n times delta phi. Because of the cosine twice. Okay. So now we can say, as I mentioned before, the minimum. So then minimum detectable phase of that delta phi minimum is related to the question, that is the average, how much the average changes, and I ask myself, how is this relative to the noise? Okay, so the question is, I would say something like, so we can say this. Let's see. So now n, in this case, so this delta n average of phi plus, or in our case, pi over 4 plus delta phi minus delta n average of pi over 4 should be larger than the uncertainty of n. So like oh, here the, you know what, let's just call it, I don't want to call it delta n, I don't want, okay, so these deltas are too much, so let's call this n12, n12, and I'll call this one an average 1, 2. So, and that should be larger than the uncertainty. So like n12 squared average. And to make things, so let's say that this is the requirement. And where it is equal, that's where we will find the minimum phase that we can detect. What are we saying? In a way, we're saying this. Look, if I'm looking at this, so this is really dn 1, 2 to the phi measured at pi over 4 times delta phi minimum should be equal to the noise. Okay, squared. So to delta squared of n12. that is the standard. No, actually this is the variance. Or in other words, now this is really just a general analysis of linear response. So what we're doing here is we're saying, look, so out of this we get that delta phi minimum squared equals delta n squared divided by dn d phi at phi 0, and this is also squared. What does that say? And this is most general. If you have something, I don't know, some parameter phi and some measurable n, which depends on phi, and it is, I don't know, it does something, has some behavior, and I want to estimate phi, and I know that I was originally here, so what I'm interested in is the slope here relative to the noise. So this is a noisy measurement, so there's noise. So here is this. Noisy measurement. So I have here a noise uncertainty which dictates some uncertainty in phase. So and this uncertainty is the minimum that I can detect, because below that I cannot tell between noise or actual change. So all that was nice. So that all that was to explain that and generally, if we want to improve the sensitivity, so we have two options. One, take this down, or take this up, or both. If you want to improve the sensitivity, you must either reduce the noise or enhance the slope, enhance the dependence. Now actually with quantum light we can do both. But first we want to see how we can reduce the noise. So I come back to this calculation. As I said, this whole beam splitter at that point, this whole interferometer at that point is simply just like a 50-50 beam splitter. So I want to calculate the expected noise here between, so basically I'll have here this one will measure N1 and this one will measure N2, and I want to calculate N1 minus N2 and the variance of that. So, okay. Can I erase? תודה רבה. I should say, however, that this is very general. No one said that this has to be a phase. It can be any parameter that you want to measure. I don't know, it can be temperature, it can be, I don't know, absorption, whatever it is. And n I don't know what that is. It's a measured quantity that depends on that parameter. And your sensitivity to this parameter will depend on the noise of the measured signal divided by the slope of the measured signal relative to the parameter that you want to measure. And we play this trick a lot. So, okay. So now, what do I have to do? Okay. So I can say that. So now I want to calculate this, so I'll erase everything else and what targets are. Oh. So, as we said, we have here, this is a coherent state, that's fine. Now here I have a 50% beam splitter, that's also simple. And what is happening here, those things I know. This is just measuring the number of photons and taking the difference. So this is measuring N1 and this is measuring N2, that's fine. And here what? I have vacuum coming through, but then first I have a parametric amplifier. So this will be a parametric amplifier that generates squeezed vacuum. So now, so I can consider, I'm not going to think about that. I'm going to say something like, okay, so here I have an operator. So this would be A1. This would be B1. And then here I'll have an operator that is, say, B2. Now we know, so I don't need that. Here there's going to be squeezed vacuum, but I don't need that because I know this is an OPA with a gain of G. So I know what is the relation between the input and the output of a parametric amplifier. So B1 equals what? A1 hyperbolic cosine of G plus A1 dagger hyperbolic sine of G. If you remember, it had to do with the fact that the parametric amplifier amplifies one quadrature and de-amplifies the other. We've done that already. Now, okay. And then what happens here? Well, we know this one generates 1 over square root of 2, I don't know, B1 plus B2. And this one here is the same with the minus. So, I don't know, let's call that C1, this one C2. So, okay, so what we measure is C1 dagger C1 minus C2 dagger C2. This is what we measure. Now, that equals, well, okay, so half B1 dagger plus B2 dagger times B1 plus B2 minus half B1 dagger minus B1 dagger minus B2 dagger times well, I can write that. But we are, and yeah, we did that before, so we know what that is. So this is like, eventually this is B1 dagger B2 minus, plus B2 dagger B1. Agreed? I think so. Yeah, here we have mixing terms which are like this, and here we have the same mixing terms again. And every time it had a half, so now, but as we said, we can now say that, okay, so this is actually, B1 is fine because B1 operates on alpha. B2 is not yet fine because this is not, we need to figure out this one. So this equals like, okay, B1, sorry, B1 dagger is A1 hyperbolic cosine G dagger plus A1 hyperbolic sine G times B2. I was taking B1 and making it a dagger plus B2 dagger times A1 hyperbolic cosine G plus A1 dagger hyperbolic sine G. Okay, so this is the measured quantity in terms of the input operators. And now, of course, so now we want to calculate, okay, so I can calculate this delta n average, which is, well, it's alpha in mode 2 and vacuum in mode 1, multiplied by this delta n operator. But we know that this is going to be 0. I'm not going to calculate. We've seen that enough times. And actually you can see that none of these will ever produce anything that is not. And then, so now we want to calculate this, okay, sorry, we call that one before N12, just to avoid the delta. So this is N12 average. Sorry that I try to. And now, okay, so this on average is nothing, so we want to calculate this, N12 squared average, and that is, okay, so now we have alpha and vacuum, and then what? Okay, this plus that squared. So we have here, we're going to write A1 dagger B2 hyperbolic cosine G plus A1 B2 hyperbolic sine G plus B2 dagger A1 hyperbolic cosine G. You know what, let's just collect all the hyperbolic cosine G together and hyperbolic sine G together. So this hyperbolic cosine we get from this and this. So plus B2 dagger A1, this hyperbolic cosine G, and then plus what? A1 B2 plus A1 dagger B2 dagger hyperbolic sine G, and all that is going to be squared. Now, and that operates on alpha and vacuum again. So, calculate this. Now let's see, where will anything be interesting? So, the only thing that has the probability let's see. Yes. I want to see if I can automatically collect all the important terms. So, this first, we can automatically operate B2, right? I mean, B2, there's nothing. Actually, I can even do this. Look, B2 operates on alpha. And when B2 operates on alpha, so it can either operate on, if it's B2, it can operate on alpha to this side and generate alpha. If it is B2 dagger, it can operate to the other side and generate alpha star. So I can just do this. I can throw away the alpha on the here, and then instead of B2, I'll just write. So this is simply vacuum, and then here we'll have A1 dagger alpha star. Sorry, not star, this is alpha, plus alpha star A1, hyperbolic cosine G, plus A1 alpha, plus A1 dagger alpha star, hyperbolic sine G, and all that is going to be squared, and that operates on vacuum. So we already operated on alpha and everything's fine. And now, all we care about are the situations that give us A1 and A1 dagger in the right order. So where will we get? So now I'm going to square this. Where will I get? So there's going to be here from this, what will we have? We will have here hyperbolic sine squared times this squared. But out of this, there's only one term that is relevant, and that is A1 dagger alpha absolute value squared. So here we'll have alpha absolute value squared A1 dagger. That's the only term that comes from here. All the others will fall. Does it appear twice? No, because the other one is the opposite order, and they don't commute. So yeah. We have here A1 dagger. This is the only one that is important because A1 dagger A1. This one falls out. Well, out of here, we will also have, and there's going to be also a mixed term. So out of here we will have, again, the only term that will contribute is when we square this. So we will have from here also alpha absolute value squared. Also, yeah, A1 dagger hyperbolic cosine squared. And then there's going to be a mixing term. Let's see if that mixing term ever gives something of interest. I think that the answer is yes. So let's see. We have this multiplying this. From the first term times the first term, they are in the right order. So I think eventually we will have also I think we will have, let's see, is it twice? Check me if I'm right. Hyperbolic sine g plus times hyperbolic cosine g. I think we will have all those. And this is, of course, operating on vacuum on both sides.
Why absolute value
Of what?
in the middle term?
Why absolute value of alpha squared?
Would be
You got a good point. Let's see. We will have this times that. You're right. So what we should have here, we will have here plus alpha squared plus alpha star squared, right? Now, each one of those terms just gives 1. So, okay, so now I can so this basically equals okay, so this is just 1 and all of those are 1, and all we have is alpha squared times hyperbolic cosine t squared plus hyperbolic sine squared t plus alpha squared plus alpha star squared times hyperbolic sine g times hyperbolic cosine g. Now, this is hyperbolic cosine of 2g. And this, I think I'm missing a 2. I would have liked to have a 2 here. No need of a 2. So this is half hyperbolic sine of 2g. Now, okay, so now we have a result. So we have here, so that is overall equals alpha absolute value squared times hyperbolic cosine of 2g plus, let's write it like that, alpha squared plus alpha star squared divided by 2 hyperbolic sine of 2g. Now, so now things depend on this. This is almost this. Well, the sign will make a difference, or the phase will make a difference. In any case, so this is a real number. And I think it can change between this maximum. So if alpha is real, then what we have here is, so when alpha is real, so this will be for alpha real, and I think the other case is alpha imaginary. For real alpha, all it is just alpha absolute value squared times hyperbolic cosine plus hyperbolic sine, and hyperbolic cosine plus hyperbolic sine is exponential growth times e to the 2g. But if alpha is imaginary, then this this one is negative, this one is also negative, and then wait. So if alpha is imaginary, then this is a minus, and this is, well, also a minus, because, okay, so here, yeah. So in this case, we will just end up with alpha absolute value squared e to the minus 2g. So this is so here we see what we wanted. So this is the reduction of noise. It depends on the phase of the local oscillator, or if you want, it depends on the phase of the gain. I mean, the parametric amplifier also can have. If I would change the gain is a number, it's real, but it can also be negative. If the gain would be negative, then, okay. If the gain would be negative, then the minus sign will be here. And then, of course, this will be the one that is diminished, and this will be the one that is amplified. So we can see that, directly from calculation, indeed, doing this, and as I said, this is relatively simple. We start with vacuum, and then we can we can reduce the noise. And I think that yeah. And it seems like so if you remember, so that means, so here we calculated that noise. So coming back to here, I would like to say that this so I can say that this quantity n12 is going to be equal to the average of n12, which is simply 0, plus or minus the noise, and the noise is alpha squared e to the minus 2g, well, square root, because that was the now alpha squared is the average number of photons that comes out of here. So we see that this is going like square root of n times e to the minus g. So yeah, the higher parametric gain we can have, the more reduction we could have that. And this is what we called the short noise limit. If you remember, when we calculated an interferometer with coherent states, so this is the way most people understand the usefulness of squeezed light. They say, so that's where usually the understanding stops. Most people say, okay, I know what to do with why squeezing is good, because it can reduce the noise, the measurement noise. When we squeeze, and another thing, and that is, in a moment I'll say that. So, okay, we just mentioned we can improve the sensitivity, and to improve the sensitivity, we should reduce the noise. And how can we reduce the measurement noise? We will introduce through the unused port of the interferometer squeezed vacuum instead of vacuum. And by doing that, we will reduce the noise of one quadrature. Which quadrature? The quadrature that we measure, because this, as we said, this is very much like measuring. We already mentioned that this is effectively like measuring quadrature. So we are measuring that, and yeah, that's it. Now then, the point is, that it doesn't have to be like that. And now I want to spend a little bit of time on another way of doing this. This has to do with what you did with Saab, I think. So I'm not going to go too deep into SU11, but I will explain a little how it can work. So, can I erase the damn thing?
Of course.
Tough. So, now, no beam splitters. We don't need any beam splitters. All so now we're talking about SU11 interference. I think Sar mentioned it a little bit, but let me say it the way I understand it. An SU11 interferometer is basically two parametric amplifiers as a gain G. It could have a gain G1, and this one could have a gain G2. And just one input. So here I don't know what I introduce. I can introduce, well, let's start with assuming that what we have at the input is nothing. And then what do we say that is happening here? Okay, so this comes into that, and then it comes here, and eventually we just measured it. So those are just two parametric amplifiers in cascade. But in between, I'll also add a phase. And this phase is what I would like to measure. So now, let's see. So I can think of this, mathematically. I can say here I have A0, and here I have A1, and here I have A2, and here I have A3. And eventually what I measure is N3, which is A3 dagger A3. This is what I measure. And then I can write, well, you know, this A1 equals A0 hyperbolic cosine G. Let's assume that the gains are equal. Plus A0 dagger hyperbolic sine G. And then I could say, but this A2 is just A1 e to the I phi, because there's a phase. So that's what the phase does. And then I can say, well, A3 is simply A2 hyperbolic cosine. So that was G1. And this one is G2. I can do that. And now I can start setting elements in. And I can express by this way, I can express the output operators in terms of the input operator. It will be a function of G2 and G1 and the phase. Now, okay. And we'll do that in a moment. But let me first think of what is actually happening. I mean, we know we have a very good representation, geometric representation of what squeezing does. So it is like if I think here, what did I have? I had vacuum. So the input state was just simply like, if this is X and Y, that's the vacuum. So that's. And then what did the first OPA do? It squeezed it. So if this was vacuum, what we will have here, we will have, well, I don't know which way are we, I think we're stretching X and we're reducing Y. So that's what we'll have. We'll have squeezed vacuum. This transforms into, this is vacuum, and this one is squeezed vacuum. Now let's think, forget about the phase for a moment. Okay? If there is no phase, then this is just another parametric amplifier. Now, let's choose G2 to be equal to minus G1, okay? So let's take that specific case. So this one is G and this G2 is equal to minus G. So let's just write it like that. So this one is like minus G. What does that minus G mean? It means that the gain is opposite. Or it means that it has, now, as we said, so this will, if those two gains are equal, then this one is stretching, the other one is just doing the opposite operation. And eventually, we will end up back with vacuum. So here we have, if this one is, this is the OPA operation. This is OPA 1 and this is OPA 2. So we'll start with vacuum, we'll end up with vacuum. But if there is a phase, then what phase does is rotate. Right? So if there is a phase, then this will look like that. This is and then when we operate with this one, so we anti-squeeze, so then we will indeed reduce this back to vacuum, but this extra in the other quadrature will be stretched a lot. So this will generate something like, I don't know, it will be like this. So this is with phase. So now what is the point here? Okay.
Can you explain again how the anti-squeezing work with the face?
Yes. Well, look, all you do is you take the image that you have and you stretch it in the stretched quadrature and squeeze it in the squeezing axis. So, what happened was originally I squeezed like that and then again in the other direction. So if nothing happened in between, I'll start with a ball, I'll end with the same ball. But if here in between this pita was slightly shifted, then when I will squeeze here, I will practically get back to something that is about the same ball. But at the same time, I'll be stretching this dimension. And this small angle will actually become bigger. So let me say something like what we're doing here is we are stretching here and we are contracting here. And in this one, we're doing the opposite. We're stretching here and contracting here. And now you can actually visually see why the slope got bigger. We're not going to have any less noise in this kind of thing. What we will have is a much larger effect of a small phase. Usually when we had a phase of phi, then it operated on the output like with sine phi or sine squared phi, but there was nothing else. Here, the angle, so what is important is that here, this has a phase amplification. This amplifies the phase. A small phase does a big change because a small phase mixes the two quadratures. It generates a little bit of this quadrature that is now going to be stretched. Without the phase, you go back to vacuum, which is no photons. And with the phase, you go back to you stretch it a lot. So the number of photons that you're going to have is much more than, I don't know, 1. Because this amplifier, it is an amplifier. It amplifies one quadrature. And therefore you take the quadrature that encodes the phase information. The phase information is now encoded in the y quadrature. And what do I do? I'll stretch it. And then in this case, we will, so that's why, so like here, I would say that with phase, so we have here phase is encoded in quadrature y. And here, we're stretching y. So now we can actually do the calculation, but you know what? I think I'll leave the experiment. I'll leave it for you. So you know, okay. So I can write that. You know, I told you that this is minus g. So let's put here. So this is hyperbolic sine, and then there will be a minus, and here will be a g. So this was like saying, okay. So I said like those would be g and minus g. So you can, of course, you can calculate that. So A3 equals A2, but A2 is A1 e to the I phi hyperbolic cosine g minus A1 dagger e to the minus I phi hyperbolic sine g. And this equals A1 is simply A0. So this equals A0 hyperbolic cosine g plus A0 dagger hyperbolic sine g times e to the I phi times hyperbolic cosine g minus A0 dagger hyperbolic cosine g plus A0 hyperbolic sine g times e to the minus I phi times hyperbolic sine g. And now we can collect terms and okay, we'll have yeah. maybe I'll do it. Let's do the collection quickly. We will have here hyperbolic sine yeah, hyperbolic cosine squared g times A0. And that's it. Times e to the I phi plus, minus hyperbolic sine squared g times e to the minus I phi times the same a0 this multiplies a0 and then what plus, let's see, a dagger will have a0 dagger time hyperbolic sine g hyperbolic cosine of g times e to the I phi minus e to the minus I phi. I think that's about correct. And you can see why there's an interference here. The phase makes a difference both here and there. So this is like 2i sine phi, and here we'll have something. Okay, and then so we can do the calculation, and I invite you to do it. Actually, I'll give it to you as a home exercise, so you will have fun. I do think it's an easy one, and now, and the main thing is that in this case, that's actually a good thing. Why is that good? Because, you know, previously what did we have? We had a measured quantity, and what we saw was, the quantum noise of that measured quantity is going to be reduced. Okay, but can I measure it? You know, okay, here we are, in theory, yes. In practice, well, it depends. Is my detector good enough? Does it have high enough quantum efficiency? Does it have low enough noise? Such that I will not be masked by other noises. So, like, so this is, in general, or let me put it like in another way. So before, we had something like, we wanted to measure two intensities and take the difference between them. So, yeah, we know what? Okay, in a moment. I'm thinking and thinking again, but eventually I'll come up with the best way to explain. I have two ways to explain why this is good, why this is better. So first, there's this. This is something that every good engineer knows. And some of you are good engineers, or maybe one day. And that is that if you want to measure a small signal, first of all, use an amplifier and put that amplifier as close as you can. So if you have an antenna that brings in a very small signal, you put the very first amplifier very close to the antenna. Why? To increase the signal very quickly above other noises. Now, and in a way, this is what we're doing here. Here is our information. It is a small phase. It's a small tilt. What's the best thing to do? The information is encoded in Y. If you want to measure this, best thing to do, amplify it before you measure. So that's one reason why this is good. Generally, it is good to put an amplifier before you measure, because then you take out of the equation the detector noise. Detectors are always noisy. Detectors have dark count, meaning they generate signals even if nothing is there. Detectors are, well, they have inside amplifiers, they have all kinds of electronics inside which will generate noise. So now, if you want, what did we have before? We said, we had quantum noise, and now we reduced the noise. Good, great, but can my detector measure that reduced noise? Could it even measure the noise before? Most detectors are not shot noise limited, because their internal noise is larger than the optical noise. So they cannot. So if you want to say, look, there's the shot noise limit of the classical interferometer, and I will reduce the noise below the shot noise limit, and then I'll be able to measure phases that are even smaller than the shot noise limit, then the answer is great, but is your detector good enough to even measure the shot noise limit itself? The answer is, in most cases, no. Most detectors are not. And some are. You need to have a really good detector, really quiet, that will be. And you can find such detectors. I'm not saying that this is not practical. It can be done, but it's hard. And here we say, no, well, I don't know. Maybe the detector is shot noise limited, maybe it isn't. What I'm going to do is I'm going to leverage the squeezing operation itself to amplify my signal before I measure it. So instead of using the squeezing to reduce the measurement noise, I'm using the squeezing operation to amplify the measured signal. And that's why in an SU11 interferometer, if we calculate, same thing, we're going to calculate what is the minimum phase that we can detect. And we say, well, this is the, delta N3 squared divided by dN3 to d phi at phi 0 squared. This is so what happens here is that it exists. It's not small. You see, this thing is noisy. There's a large noise ellipse here. If I will calculate the overall intensity out of this, it's not going to be small. So there's a noise. But this is growing even faster. So that's what we gain. And this, as I said, will leave you as a home exercise. I'll make sure that you get it. Tov, I think now is a good time to take a stop and then stop talking about interferometers and squeezing and stuff like that and start talking about other things. So let's talk a little bit about entangled photons, why they are entangled, and so on. We want to talk about entanglement. Now, entanglement is a huge subject. We can have an entire course discussing entanglement. But in general, entanglement comes from the fact that the quantum superposition lives. Okay, so let me tell you bad definitions of entanglement. then we'll try to somehow figure out something that is not so bad. You know that, if we think about just a single two-level atom. So that single two-level atom can be either in state up, or excited, or down, or ground, like E and G. That's what we had before. But of course, it can have the quantum state can actually be a superposition of those. So one particle. So it has the basis has two states. Now if we go to 2, then the basis states are now, well, either both of them are up, or one is up, the other one is down, or one is down, the other is up, or both of them are down. So we have 4 options. And the superposition now, so if that was like a single state, so psi of two photons is now like, well, it has C1 plus C2, plus C3 plus C4. So this is, the superposition lives in a, so in this case it's a, superposition is a vector in a 2D space. But here this is a vector in a 4D space. And in general, when we will go to n particles, we'll see that the Hilbert space is 2 to the n dimensional. So, and this is a superposition in Hilbert space. So the superposition explodes. And okay, so, and then if superposition is weird with a single particle, it becomes completely crazy when we look at larger dimension, at more and more particles. So, in general, entanglement is a many-body property. Many can be 2. And it is the fact that, and then people say something like, well, entanglement is like inseparability. An entangled state is a state of 2 particles that cannot be written as a multiplication of 2 single particle states. Okay, yes. That's true, but it doesn't tell me anything about what entanglement gives me. It's a negative definition. And it doesn't even tell me how to identify, how do I know if the state that I have is now entangled or not? Is it separable or is it not? I don't know. And also, separability is a question of basis. Like, as I'll show you in a moment, a state can be separable in one basis and inseparable in another. Now, so now we want to talk about it, but in a way. So usually people say like that entanglement equals inseparability, saying that like basically saying that you cannot, if you want to write this psi of two body, cannot be written as psi 1 of body 1 times psi 2 of body 2 for the so the two bodies, okay, but that, I hate this. So first let me show you something. Well, you've already learned a little bit of quantum optics. So let's think about, modes, electromagnetic modes, they can have a quantum state. Right? An electromagnetic mode can be in vacuum, so there's no photons in there. Maybe there's one photon in that mode. Maybe there's a coherent state in that mode. So every mode has a state. Let's assume that all we can have is either one photon or zero, okay? So here I have two modes. This is mode 1 and this is mode 2. Here there is one photon, here there is zero photons. Is that state separable? Well, looking at it like that, the answer is yes. This state of the two mode state is like one photon in mode 1 and zero photon in mode 2. That is separable. And then, what do? I'll put a beam splitter and mix them. So now, well, I can show you very easily that, I don't know, now there are two new modes. This is like mode 3 and mode 4. There are also two independent modes. What is the state of those modes? Well, the answer is we can calculate, but I tell you that in this case, the state in terms of mode 3 and 4, psi of the two mode, is either there's 1 over square root of 2 chance of there being one photon in mode 3 and zero photons in mode 4, or the other way around. You could say, well, but this is inseparable. But it's the same state. All that happened was that I went through a beam splitter. And if I want, I can play with the phase and I can make this minus, and it could be. So this seems like, well, here, I don't know what is the occupation of mode 3. It can be 0 or 1. And I don't know what's the occupation of mode 4. It can be 0 or 1. But if I measure mode 3, I will know mode 4. Because the photon, if I see the photon here, there's nothing there, or the other way around. So is this an entangled state? Or not? So I really hate this definition. I never understand it. Oh. No, I think you're taking Emmanuel's course, right? Ask him to define entanglement. Let's see what he brings up. But let's talk about but entanglement does or bring with it surprising results or things that can be non-classical. In this, so let me, so let's start with where entanglement started. So let's talk a little bit about EPR. So and so yes, 3 Jews. Yeah. So EPR has to do I'm sorry. Oh yeah. Okay, so in EPR the concept is as follows. Okay? So I have what Einstein had in mind was to say, look, I have a particle. He was thinking about a particle. And then this particle was moving with some very well-defined momentum. So I don't know where that particle is, but about that I don't care. Okay, so say that it was, or it was sitting in some well-defined space position, but and then at some point it got it was split into 2. So here it was like, I don't know, broken, and those 2 particles flew away, and they had, this one had P1, this was P0, this one had P2. Then we can say, of course, P1 plus P2 equals P0. And specifically, I can think about, in this picture, this, let's call this one small p1. That's just the big, the vector, this component of this one and this component. So that just the y component So this is just like P1 plus P2 equals 0. So this is just the y component. In fact, P1 plus P2 is equal 0 if this P0 was perfectly well defined. If this P0 was not perfectly well defined, then the uncertainty of P0 will be written here. Now, but I can also ask, so, okay. Then, or the other thing is that I don't know. So what about and now about, okay, so okay, so what are we saying? Look, on this particle, I know its momentum. Okay, I know its momentum practically in all dimensions. So I know it's P1, Px, Py, Pz, which means that I don't know where it is. In terms of uncertainty, that means that I don't know what y, x, y, or z of that particle is. But at some point, it broke out. So, and at that point in time, those two, so it broke out. Now then, that means that if I ask, where in space did it happen? I don't know. So I don't know what y1 is or y2 because it's the same as Mr. y0. But what I do know is that both of them separated from the same point in space. So it's funny now, okay, so I can, and in a way, I will be able to measure that in a moment. So okay, so we say, so this is like saying, okay, so in this case, I have an interesting situation where I have two particles. I don't know neither the momentum or the position of each one of them. But I do know that the sum of their momenta equals to the momentum of the father particle. In this case, 0. And that their position difference is 0 because they were emitted from something. Now, well, you know, okay, so there is this more thing of uncertainty. We constantly think about that. Now, we know that quantum mechanics tells us that you cannot know both the position and momentum of a particle. Why? Well, then the y becomes a little bit vague. You get all kinds of responses. The most common response was that, well, you know, if this, when you measure the position of a particle, you need to, how do you know where it is? Well, you need to scatter something off it. Okay? So, for example, and then, now, if I want to, and this has to do with practically waves. So if this, I want to identify very well. So I can say that I need a very short wavelength of whatever it is that I scatter in order to measure. A short wavelength means high momentum. That means that this scattering event, the better I try to understand where that particle is, so I will have to scatter a higher momentum particle off it, and this scattering will give it a kick that is uncontrolled, and therefore I will have I will not be able to tell what its momentum was because I just ruined it in my measurement. So the problem is the measurement process. Because of the quantum measurement, we cannot know both position and momentum. But then Einstein didn't like that, because he said, well, come on, this is a problem, this is your problem. Your device is bad. But it doesn't mean that the particle had a momentum and a position. It was a ball, it was rolling slowly in that direction, it had a momentum. And then you tried to measure and you kicked it. So you don't know where it is, but it had a momentum. So Einstein said, well, but let me show you how we can measure this. Well, look, if we do that, then, okay, I'll take this particle. And what will I do? I'll measure its momentum. Okay, so I'll know its momentum, but then I know the other one as well. The other one is moving that way. Okay? Well, it is moving that way, but I can think of imaging, or I can think of deducing. I can measure its position here, but I know its momentum now already, right? So I can just roll it back to where it was. Because I've just learned. I measured this one, so I know its momentum. I'll measure the position of this one, I'll know its position. But I know the momentum because I measured the other one. So then I'll be able to tell the position of both of them. Okay. So we can use, so this is the paradox. The paradox assumes that the particles do have a position and momentum that they know. It's only my measurement limitation that does not allow me to measure both. And then I'll be able to know both of them. Now, quantum mechanically, this does not work. And it tells us that quantum mechanics is non-local. The fact is that the thought that I'll measure P1 and then deduce, and then here I'll measure this does not work. Now, Bohr, who was the father of quantum mechanics, said, no, you're wrong. You can't do that. It doesn't work. When you measure, the state collapses, and then you cannot anymore measure the once you measure the momentum of one, the state collapsed, and you cannot measure the other. And then those two giants argued for 30 years. Well, no, well, each one of them died at some point. And then the rest of the world just gave up. Now, what is the problem? So let's say something about, and that is important to say something about what is the why is it so hard to understand whether, I don't know if the state collapsed or not. So we have So it was something like this. So Einstein was saying something like, look, each particle does have a position and momentum. As we said, it is rolling somewhere with some momentum, with some position. It has it. The problem is yours. So it says that basically that there is some hidden variable. Each particle knows. So Einstein is something like saying, like, look, there's a hidden variable. What is that? When those two particles spread, when they split, they made a decision. They made an agreement between them. And that agreement was, okay, so, I mean, they figured out, I don't know, they flipped a coin, they did something, and now each one of them knows its own position and momentum. It is just us that don't, but we don't know what they decided, so our problem is information. There's a hidden variable that the particles know. And deterministically, that determines with no ambiguity. The problem is that we don't know that hidden variable. And Bohr says, I don't know, no hidden variables. The state collapses. That basically means, and that state is non-local. The state is the two-particle state, and the two particles are, I don't know, they can be separated light years apart. So, okay. Now, so what is I want to say something like, so what's, so the question is, how can we tell? So usually at this point, people start talking about Bell and Bell states and Bell inequalities, and all those I promise that we will do next in our either Zoom or physical meeting. Well, I think that within this, you two prefer probably Zoom. You two, I don't. You prefer physical. You.
Both is okay.
Well, both are okay.
Yeah.
Well, I don't know. That's all. Honestly, I prefer to teach in the class because then you guys are constantly. I never know if you're here or completely numb. But I think. Usually I can feel the class better when I'm here. So the question was, how can we tell? Now, what is the problem? The problem is this. Okay, so the question is, how can we tell? That's one question. And two is, can we do the experiment? Okay, so then the problem is that measurements are always partial. What do I mean? If I measure, I don't know, P1, then I don't know Y1. I cannot. So this is inaccessible. And so that's one thing. Measurements are partial. And the other thing is that so that means that local measurements I can identify P1 plus P2. I can measure each one of those and I'll know the sum. And I'll see that every time that I measure, P1 gets every time a different value, but their sum is always the same. But that's all I'll identify. I can identify this or x1, sorry, we were with 1, y1 minus y2, but not both. So then I don't know. Like, okay, like if I could so the fact that I cannot measure both. Now, but if I could, this is a problem of local measurements. In a moment, we'll talk about a global one. So that means that, you know, I get partial information. Measurements are partial, or measurements provide partial information. And okay, so basically it is hard to tell whether, you know, most of you probably heard that from me at least once. You know, I wake up very early in the morning. My wife is still asleep, and it's still dark outside. So I go and I need to take a pair of socks. So I open the cupboard at night, and then I don't know which socks I take out. But so maybe they're white and maybe they're black. Sometimes they're brown, but never mind. I don't know. And I wear them also in the dark, and I wear the pants in the dark, so I don't know which socks I have. But what I do know is that my wife, she is tidy. I'm not, but she's very tidy. So she always puts the pairs of socks together with the same color. So if this sock is whatever the color is, I guess something like dark blue, then probably this one is as well. So now, what is the problem? Well, there is no problem. The socks had a color. It's only I don't know them. So the hidden variable is indeed, I don't know, there was like a random coin toss, which happened when I took the pair of socks out. And this dictated that. What is the problem? The problem is that in this case there's only one correlated feature. It's the color. Maybe my wife wanted to trick me and on purpose tied white socks to black socks. All of them. And then we know that if this one's white, the other one's black. But still, the socks have a color. And now the point is that these particles have two properties. Now, and those two properties are combined. What is the one thing that I know before I even looked? I know that the two of them have the same color. The color difference is 0. But that's all there is. There's only a color. Now we're saying, look, the position difference is 0, and the momentum sum, that's also 0. So that means that in this case, the uncertainty of position difference times the uncertainty of P1 plus P2, quantum, so what we say, okay, look, this uncertainty, this multiplication of uncertainty, it can go to 0. Does that violate uncertainty principle? No, it doesn't. Because those two are not Are they uncertainty related? The answer is no, they're not. Why are they not uncertainty related? Because, well, you know, okay, y1 and p1 are uncertainty related. y1 plus y2 is uncertainty related to p1 plus p2. There's an uncertainty relation between those two. y1 minus y2 is uncertainty related to p1 minus p2. So, but the point is that I'm telling you, look, I want to measure this one and this one. They're not uncertainty related. So conceptually at least, this can be extremely well defined. How? The mother particle had a perfectly well-defined momentum. How? Well, I don't know. Somebody really selected very well specific momenta, and then so yeah, you have a monochromatic beam of particles. Then yes, the sum of momenta is defined by the mother. And then what about the position difference? Okay, and indeed, by the way, if I know very well the momentum, the sum of momentums, then I don't know the location. Why? Well, because this will be dictated by the mother particle, and I don't know where that was. So if this is very well defined, then this is, I don't know, exploding, but I don't care. Now, and this is very so those two, they're not uncertainty related, so they can really, so they can reach zero with no limit, can approach zero but if the particles have a position and momentum, if they did. But that, okay. This can happen only if y1 and y2 are truly not defined. And P1 and P2 are truly not defined. Only the sum is defined and the difference is defined. If P1 and P2 are defined, if the particle knows its position or momentum, it cannot. So the question is so if they're not defined, but the difference that can approach, but if y1 and y2, p1, p2 are defined, then they can be defined only up to uncertainty. So that means that, you know, I don't know, there's delta p1, delta y1 larger than, well, you know, just, you know, half, and the same delta y2, delta p2 is larger than half, and under this you will find that therefore y1 minus y2, the uncertainty of this one, if they are defined, then this difference cannot, well, I don't know, maybe this difference is extremely well defined, but then this, one of them will not be. So then suddenly this becomes half, quarter. This is like what we would call a classical limit, or the separability limit. So now, okay, now we want to converge to a finish. So, and now the question is, now this is something that we can maybe think of measuring. But now let's understand what, so what did I tell you? Look, if those quantities are really not defined, I cannot know each one of them. Then this uncertainty of difference times uncertainty of some, uncertainty of difference position, some momenta, can be, these multiplications can be really zero. I can know this one extremely well, and I can know this one at the same time extremely well. But then what do I need to do in order to know both of them extremely well? I need to measure them. Now, at least conceptually there is no problem, because if I measure this, I cannot know that, but I don't care. If I can measure this, I cannot know that, but I don't care. I want to know only those two. And there's no uncertainty problem between them. What is the problem? The problem is that I need to make a global measurement. I need to be able to somehow measure the sum of momenta without measuring the individual momenta. That's a global measurement. This is somehow looking at the pair of of particles and say, well, I don't know and I don't care, and I will not even be able to tell what is the momentum of this one or this one, but I'll know their sum. I'll measure their sum somehow. And the other thing is, and then if I can do that, great, then maybe, then I didn't disturb the possibility. If I can measure this, I'll get this information, and I will not disturb the possibility of knowing the position difference. But again, I'll need to do that in a global measurement, in a measurement that measures the position, not the position of that one nor the position of this one, but only the difference of their positions. Surprisingly, this can be done. Such a global measurement is something that can be done. And we can show, we actually did that last year. And we can show that we can beat the separability limit, and that we can, that requires Okay. So, if we can make a global measurement, then we'll be able to tell the difference between non-entangled, separable situation and an entangled, unseparable situation. But for that we need global measurements, and usually people don't have that. Can we identify entanglement based on local measurements? Can we do local measurements and identify the fact that those two particles are entangled and not correlated, not just correlated, that there cannot be any hidden variable that dictates the result, but the results are correlated better than the best separable or the best unentangled or correlated case? The answer is yes, and this, not now. So this is what Bell understood in 1964. And about what Bell did, we'll discuss next time. So the Bell inequality and how we can deduce also from local measurements the existence of entanglement, that next week. And yes, and I think that, yeah, well, we'll have it in Zoom probably. And I'll
Tell you what,
send you an email.
we
What?
probably won't attend this.
You won't attend anyway.
Because we have
so-
the next day, so you just do
Uh-huh.
what you want.
Okay,
Prefer.
okay. So we'll have it in, we'll have a physical meeting.
It's the last lecture.
No more.
Yeah.
Oh, there was one thing that I did want to say, but next time. I did want to connect that to squeezing and parametric gain. Actually, and the only thing that I can say about that for now is just the fact that what are we talking about here? Pair production. Generating, if you have a way to create a pair of particles, and this is somehow related to this. But what is squeezing? We discussed it. Squeezing is the emission or annihilation of pairs of photons. So just a parametric amplifier. Well, a parametric amplifier in high gain creates or maybe annihilates many pairs of photons. But if you take the gain very low, then it will most likely do nothing, and sometimes it will create a pair. So actually, parametric gain at low gain or squeezing at low gain and entanglement generation is the same. Remind me, I'll mention that and explain that in the beginning of next meeting. להתראות.
תודה רבה.
בבקשה. נו, אתם התחלתם לעשות דברים במעבדה?
מחר.
אחר מקום בית.
מחר. כן יהיה לעשות.
So, should we start? Let's start at the time. Yeah, sure, let's start. Start 1 minute early, finish 1 minute early. Okay, so today we're going to continue what we did last time by exploring the SC11 configuration. If you don't remember, we said, I made pen. Right? Well, we said that having two OPAs, two parametric amplifiers, squeezers, pump, and then some PC mode with phase component on it can give us some interference. right? That we can measure. But as you saw today in the lecture, this component, this squeezing component, doesn't have to work for only the degenerate case. When it can work also in two-mode cases, in signal and light, when you generate another beam here. So that blue is dead. I'm gonna use it. Generate another beam. Okay. Okay. And before we seeded this mode with vacuum, today we're actually gonna try to amplify it even more by seeding it in some coherent state alpha. So our starting mode now.
What is the purple way?
This will call the
Signal.
the red will call the signal, and the purple will call the idler arbitrarily, right? Yes. Do you need me to show you again the transformation for two mode, or did you do it with RV? We'll do it anyway in a second, but if you need a recap of two mode squeezing, we can do a short recap for it, or even squeezing. No? Fine. So now our input mode, why am I writing in red? Why is it so hot in here? Okay, so now the input mode would be alpha 0 or AS tag AS plus alpha. Right? We saw that the displacement in the field is equal to just an addition of the constant to the operator. So now we want to see what will be the output from this from this SU11 system. Specifically, let's look for a second. S dagger of G, RS phi. Notice RS means I'm just giving phase to the S mode. And S dagger of G, S tag, then S of G, R S phi, S of G. Right? Going in, towards out, in then out, we get S dagger G, R dagger S phi times A S tag cosh G plus A I dagger sinh G R phi S G or S dagger of G R sorry A S tag cosh G e to the I phi plus A I dagger sinh G S G, right? Overall, this would be equal to, note that, no, 1 second. Now, next, we do it again. So you have cosh G S tag plus sinh G AI dagger of times cosh G e to the I phi plus, now note that for any transformation O dagger A dagger O equals O dagger, sorry, O dagger A O dagger, right? Just replace as a dagger. So transformation on I dagger will just be the dagger transformation on I, which is exactly the same as transformation on S, just replace the notation. It's going to be plus cosh G AI plus cinch G AS dagger, all of that conjugated. Cinch G, sorry, not cosh. Cinch G. Overall, AS out to be equal to, after all the organization, which you will see fully in the notebook, equal to where is it? AS tag cosh G squared e to the I phi plus cinch G squared plus AI dagger cinch G cosh G 1 plus e to the I phi. Now we need to do this exact same process to the idler because we want to know everything that comes out, so we'll do the same to the idler. And I'm gonna skip all the steps and just give you the final result. First of all, we know that it will generally look almost the same, just with replacing the notation, since idler and signal are arbitrarily chosen. But the phase will also move because we're only adding phase to the signal. So the phase will not be symmetric, but everything else will be symmetric. The full derivation will be in the notebook that I couldn't upload yet, since for some reason the university blocked my password or something. I don't know, and the change password doesn't work for me, so I don't know when I can upload this. Yes, this tutorial notebook. Plus dagger G cosh G 1 plus e to the minus I. Okay, so the results. And now to continue to analyze our system, we need to find the sensitivity. Reminding you from last tutorial, and sorry for that, sensitivity equals minimum delta phi equal to delta squared phi delta squared some measurement divided by absolute value of derivative of phi of the measurement squared. Sometimes you take this entire thing into a root, sometimes you take it squared, depending on the convention that you're using. Alright, now this will be a bit long for the tutorial, so we'll find sensitivity itself in your homework. Like
You call this
like
S? Sensitivity.
S, sensitivity, yes. Yeah, so this will be a bit too long to do right now in the tutorial. Luckily for you, and more likely for me, you'll have all the time in the world in your homework to do it. So we'll just start. You know, I like to help you, so I'll start and we'll do it ourselves. So first of all, we need to decide on our measurement. We have a few measurements we can take. For example, we can measure the signal, we can measure the idler, we measure both, we can measure the difference between them, and so on and so forth. Bon appetit. Okay, whatever, I don't mind. So let's just pick one and start. Let's see what happens, and then we try to think about what we're doing. First walk, then think. So let's start with NS. Why did I choose to start with NS? Because we're sending the signal So it's the stronger mode. We expect to see something good in a very bright mode, in the mode that has a lot of power in it. Let's see if it's actually true. So this will be equal to AS out, dagger AS out. Of course, this would be equal to AS tag dagger cosh squared G e to the minus I phi plus sinh G plus AI sinh 2G 1 plus e to the minus I phi multiplied by 2. Note that sinus hyperbolic G times cosinus hyperbolic G equals to 1/2 sinus hyperbolic 2G. I just use this equation here. And then, of course, all of this times the non-conjugate part, square G, the I phi plus sinh G plus 1/2 I dagger yes sinh G 1 plus e to the I phi. Okay. Now we'll do as we always do. We try to see what cancels out. Well, we have a creation operator here at the start, but it's not really a creation operator. It's AS dagger plus alpha conjugate. So AS dagger removes, and this one will just be left with alpha. So overall we have alpha here, and then we see that this alpha conjugate, for example, does not mix with the idler term, since you will have idler operating on the left, which will be 0. So we have these two terms multiplying each other, and these two terms multiplying one another. So we'll have, first of all, the two terms here. We'll have cosh squared G e to the minus I phi plus sinh G squared. Oh, missing a squared over here. Cosh squared G e to the I phi plus sinh squared G. Right? And then plus 1/4 sinh 2G of 1 plus e to the minus I phi 1 plus e to the I phi. Right? Okay. So the first time we have the cosh times cosh would be cosh to the power 4 G plus 2 sinh power 4G. And then we have cosh squared times sinh squared and sinh squared times cosh squared. Each of them will be with the e to the minus I phi plus e to the I phi. So we'll get 2 cosh squared G sinh squared G. Oh wait, I forgot the absolute value of alpha squared. Yes. So there's an absolute value of alpha squared here. Time cos phi. Right? These two terms multiplied with one another would be 1 plus 1 plus e to the minus phi plus e to the plus phi. So it will just be 2, 1 plus cosinus. So it's 1/2 sinh squared G 1 plus cos phi. Okay? Good. So I'm gonna rest this part. Now I can organize it a bit more, but we mainly care about the derivative now, since the sensitivity requires derivative. So let's do the derivative first and then organize it, because it will remove a lot of terms. Okay. So taking the derivative, this term and this term will go to 0, plus this one will go to 0. We take a derivative in phi. So we just have this term right here, this term right here. So we have d phi of average and s, average to be too high, d phi form. Right? It's going to be equal to minus 2 cosh squared g sinh squared g times phi plus 1/2. Oh, I'm missing 2 here. Yes, is still missing something? 1 second. Yes, and there's also still need to be a square here and here. I have it correct in my notebook, right? It's fine. Because 1/2, and this one has 2 by 1/2 squared. 1/2 minus 0 body square to g sinus phi. Now cosinus squared g, sinus squared g will just bring us the same term, so it's minus 1/2, also the value alpha squared plus 1 sinus hyperbolic sine squared 2g sinus phi. All right. So this is one option, and we see that this result is not much different from what we saw when we developed this SC11 configuration without any setting. We just see that above this vacuum 1 that we see everywhere, there's also an amplification by the coherent state level that we have. All right. So this is one option. What about measuring the ideal? We can try to measure the ideal. I can write it all down on the board, but there's a simpler solution. Can anyone guess what would be this delta phi and s and I? What would it be? Anyone guess?
Transcend cosine.
Huh? You know what? Let me give you a hint. You know what? No, actually, sorry. Say it again.
Cent cosine. Hyperbolic sine to hyperbolic cosine.
Almost, but no, not actually. Let me give you a hint. Let's look again at the Hamiltonian that generates to a squeeze state. All right? H equals I/2 AS dagger AI dagger minus AS AI. Right? What does this Hamiltonian tell us? You saw this Hamiltonian, right? Avi showed us. I hope. What does it say? What happens when it meets a bunch of photons?
Slide leader stays minus your non-exciting states.
What? Sorry, can you speak up a bit?
So this, the first term is your
You create and generate.
So last one is no generate, so just
Generate 1, and here you annihilate 1, 1. Right. You're correct. So we either generate pairs or destroy pairs. So if we see that we changed an S by this much, this equation, how much would an I change? At the exact same amount. Since let's say I measure and I see that we generated 3 photons on the signal. Well, I know that we generated 3 photons on the ideal as well. So even without even without calculating everything, we see that we can extrapolate that this change, this derivative, will be exactly the same. Both of them will be exactly the same, even though the overall number of photons won't be the same, because we started with a coherent state on the signal, right? Everyone clear about this? It'll just be in the notebook. There's the full calculation both for the NI. I just wanted to do a little trick and show you that it's equal without needing to prove it, without needing to calculate anything. Anyone understand? Even you in the front in the phone?
Target.
All right. So the change in signal, change in lidar is exactly the same. Can we actually do some other measurement? Well, of course we can. We have a million different quadratures that we can measure, some subtraction, addition, multiply the two intensities, etc., etc. So from all these options, let's start with something that we know. We remember that when we did the Mach-Zehnder, we have, we'll write it here, beam splitter, mirror, mirror. We have a beam go up, up, up. And then we take the subtraction of the two intensities, right? So you can try to do this. Okay. I'm not going to do this. Why? Why am I not going to try to measure the subtraction between the two modes? No, there's an interesting result from this. I'm just saying this result will give us something that wouldn't work if we wanted to measure sensitivity. I'm going to tell you I didn't write it in the book, I didn't calculate it in advance, and I'm going to predict that it's going to be equal to alpha squared. That's it. Again, why? Well, again, Hamiltonian creates pairs. So if we started, let's talk in single photon regime instead of the coherent state, and then you can work it out. Then we can convince ourselves that it also works for the coherent state. If I have a crystal, some OPA crystal amplification of G, and I put in with one mode, let's do lower. Let's do 2 photons. Right? On the output, the 2 modes, all right, 1 and 2. Well, first of all, we have the 2 photons that we put in. They don't go anywhere. Okay? And then, let's say our crystal or nonlinear interaction generated another 4 photons. So I'm going to write them in red. Okay? And since we're creating pairs, we know that each photon created on the signal needs to have a photon on the either. 4 and 4. Subtraction between them, so we have 2 plus 4 minus 4. So you can put how many squeezers that you want, how many squeezers that you want, how many phase components that you want. This difference will always be conserved, right? And just as a little enrichment, this is why it's called SU11 interferometer. SU11 interferometer, SU11 group it comes from group theory. Is the matrices? No, yeah. Let's just say it. I have it here at the bottom. SU11 group are all the matrices of the form U, V, V conjugate, U conjugate, so that U absolute value squared minus V absolute value squared equal to 1. So they are conserving a difference. In a Mach-Zehnder, we call it an SU2 interferometer, since it preserves the SU2 group symmetry, which are all the matrix in the form of alpha, beta, minus, beta alpha and absolute alpha squared plus absolute beta squared equals to 1. Or if you want to think about it in physics term, a Mach Zehnder only have mixing components, the beam splitter, so it will preserve energy, but SU11 or squeezers are non-energy preserving. They're amplifiers, but they're not just amplifiers, they're symmetrical amplifiers. So they don't preserve energy, but they preserve the symmetry between energy or the difference in energy. So measuring the difference between NS and NI will give us always a constant, what we enter in the beginning of a system. So we can't use this measurement like the Mach Zehnder.
We need to know it like this. What does NS mean? Why do you add it to the
NS?
photons in the input? Yeah.
I don't answer what did you ask? Again?
למה אני צריך להפעיל את ה-signal photons that you created in the NS? In the why do you add
the two,
original?
right? Yeah. Well, because we can think about the amplifier as a field multiplier. Yes, this is one way to think about it. But this is a simplified in this singular photon regime. When I said instead of multiplying, I just add n photons. The fact that I added n photons doesn't mean that the photons at the beginning disappear. You can try to do this yourself if you want to calculate this and see that it will come out as the output. But the point is, the big point that you need to take for all this is that this Hamiltonian is symmetrical in signal and idler. Everything that happens to the signal will also happen conjecturally to the idler. Does that answer the question? The fact is that here in this simplified drawing, this amplifier adds a number of photons, which is 4 in this case.
So in general, the signal go with the original beam, and idler is the new generated.
You always have some, you always have this beam times some multiplication here, and then the idler beam will also have some multiplication in it. But notice that when I say S has some multiplication, it's not straight multiplication like you're used to. It's not AS goes to A times AS. No. It's some multiplication that depends on the other mode, the idler. Idler depends on the signal depends on idler. But overall, if you look, we can infer the coherence, like properties on the coherent state based on looking at the much more simplified single photon state. When you compare photon to dots and get killed by Avi. Yeah. So the point is, this Hamiltonian will generate the same difference in the idler and the signal, same change. Okay. So now, before we move on to the next, before we move on to the next measurement, I would like to take a second to think which one we should measure if you just measure one mode. We don't do any special measurement, you just want the intensity measurement of either the idler or the signal. Which one would you measure? You remember that you want to minimize this sensitivity. So the denominator doesn't matter. So we need to find if there's a change in the denominator. Now I'm not gonna do the calculation for the noise, for the standard deviation here. It will take too long, and it will take away from your homework. So I won't do that to you. But in general, I think, without even calculating it directly, I think that it's more reliable, I'm more confident in saying that we should measure the idler. Why is that? Because in the signal, we have these alpha photons extra over the idler. And these alpha photons will generate more noise. Since they are the coherent state, it's some blow up there, and we know that the noise of the coherent state is proportional to the number of photons in it. So I have some coherent state that's amplified. squeezed, and then the vacuum that's amplified. The vacuum that's amplified, we expect it to have a lower noise than a quiescent amplified. Alright, so now let me go back to the simplicity I wasn't note. Yes. So if measuring the difference wouldn't work, but it does work on a Mach Zehnder, let's do it in reverse. In the Mach Zehnder, measuring the sum, measuring the sum of the two outputs will just be equal to the intensity that you fed the Mach Zehnder, since you have energy conservation. If you measure the intensity here plus the intensity here, draw it. Wow, this is a very, very weird Mach Zehnder. Okay. If you take the plus here, you just measure all the energy in the Mach Zehnder. So we just measure a constant. So maybe we can measure the sum here. Then we can do Ni plus Ns, right? And I'm not gonna, Ns we already have. Ni for brevity, and because I know you guys want to go home early, I'm not gonna do on the board. But trust me, it's almost the same as doing an NS, right? But the results will be, I'm just going to give you the output, alpha absolute value squared, cosh power 4g plus sinh to the power 4g. Yes, those two can be written much shorter, but I don't wanna. Sinh squared 2g plus 1/2 sinh squared 2g of 3 plus alpha squared cosh v, right? And now for the derivative, the first term, the first time will disappear, so d phi I plus s will equal to 1/2 minus 1/2 sinh symbolic sinh to g 3 plus absolute value alpha squared cos phi. Alright, so it is an improvement. I need to check in my notes. No problem. Wait a second. I think I have a mistake in my notes. Yes, I have a mistake in my notes. It should be, I'm gonna have to fix it. It should be just 2 times. Yeah, this one is wrong and I need to fix it in my notes. I just noticed this one's wrong. But overall, it will be just 2 times the derivative of either one, which is expected because the derivative because this one will also be equal to d phi of Ni plus an S, because the expectation value is separable, and then will just be equal to d phi of I plus d phi and S, and we know that they're equal to one another, so it's just 2 times the first term. Okay, so that didn't bring us a lot, that didn't give us a lot, we didn't do anything, but no worry, I have another idea. So, let's go back for a second and think, why are we even using those squeeze modes, those squeezers to do an interference? Second. Why? Well, because we saw last tutorial when we did it in the generate that y equals I divided by 2 a dagger minus a. When you move it into squeeze mode, when you move it to a squeezer, y out, like say y tag, will equal y given the minus g. Right? Now, if we look at the two-mode quadratures, Ali showed you the two-mode quadratures? Alright, then I'm gonna just say it. This is how we define the two-mode quadrature. The heck? You can see that if I take this is the other one, AI dagger AS. You'll see that if I take AS in the real and imaginary quadrature x plus I and y, it will be equal to 1 over half. This one is the dagger, sorry.
Okay, show this.
Yes, he showed you. Right? Additionally, we know if we'll put in the two-mode squeezing, which I erased somewhere, y will be equal to y tag will be equal to y 2 cos g s plus sorry, this is sinh, this is cos g I dagger minus sinh g I dagger minus cos g s is equal to minus g y. We'll read the same in the two-mode quadrature. This will be the one that you squeeze. So we know that we squeeze the quadrature because it can give us better sensitivity. So what will happen if we measure the y quadrature? Now, there's an important point. There's an important point when we talk about two-mode quadrature. First of all, in one-mode quadrature, y equals y dagger. You can try to take the conjugate of this equation, it will be the same, but in the two-mode quadrature, y does not equal y dagger. Right? Take the complex conjugate of this one, you'll see that just the position of the dagger will be wrong. So we don't take y squared as a measurement. We actually have to do y dagger y measure. Right? Now this, let me see how long it is. See, this is pretty long. So I don't know. I think I'll just give you the final result. Then we'll. What's the time? 6:40. We won't call it a day, but we'll find something else to do because I don't think you're really here for all this math.
That's right.
Just you. You stay after class.
Shit.
1 plus absolute value alpha squared. The full calculation is in the notebook again. Don't worry. Just don't know whether I'll be able to upload it. The cos squared g plus sinh squared g squared plus 3 sinh 2g cos phi plus sinh 2g cos 2g 1 plus cos. Okay, the derivative equal to minus 1 plus absolute value squared alpha of sinus 3 of 3 plus hyperbolic sinus to g plus think there's a missing square here. Well, plus sinh 2g cos 2g. Right? We see again, like the first derivative, alpha squared plus 1, the sinus will be the same, but we have a much bigger hyperbolic term here. Both of these terms are actually bigger than the singular term. Yeah, so we see a much stronger correlation when we measure the squeezed quadrature itself. Yes. In your homework, you actually look at a couple of different measurements and try to analyze it all the way through, and you'll find the best measurement for this simple case for the SC11 interferometer. But you have half of it here already. Whoops. My bad. Now we can be done, or we can talk a little bit more about group theory. So this is your group theory. You really want to talk about group theory?
No.
So I think for me we're done. I'll just say one thing about group theory. Know that when we talk about SC11, we said that this is U, V, V conjugate, U conjugate. This is not a mission, and it's also not unitary. But this is still the transformation matrix for the squeeze state. This is just not equal to S. S of G equal e to the minus 1 over half A dagger S AI dagger minus AS AI. Right, this one does not have a simple matrix form. This is unitary, and the overall transformation is not unitary, but we still consider this to be the matrix to define our SC11 interferometer. That's the only point that I want to say in case someone got confused in the future. It will also be the entire extra curriculum stuff that I wrote about the group theories will be in the notebook, so you can see it when I be able to connect to the website. Right now I'm a bit locked out of it, so you can't upload anything. So you save from your homework for now, but there will be one short question somewhere later this week. I'll upload it. That's it. Good luck. Next week you have another lesson with Avi. I'm not sure if we'll have a tutorial.
This is the last tutorial.
This is officially the last tutorial, and there might be get out of here. And there might be another lesson for what we missed when me and Avi were abroad last 2 weeks ago.
Yeah.
2 weeks ago. If I remember correctly, Avi wanted to talk more about SC11 and some quantum modes interacting with the two-level system. A very interesting model. I forgot the name of it. I had it in my mind a second ago, but now I forgot the name. So next lesson will be very cool. I'm sure we'll have a tutorial. How Avi will tell you. So I think we're done. Okay.
When will be the due date for the 5th assignment?
If I remember the 5th assignment, I'm going to give you a month. I don't care.
So the same is 4.
What?
Same is 4.
4 is in a month from now.
Something. 3 weeks, 2 weeks.
It will be after 4. I will check. It will be after 4. You don't have to worry about it for now. And soon Avi will give you probably after the next lecture, maybe 2 weeks after the next lecture, he will give you the final assignment, which is the test for the course. You don't have a test class. We have a work that you have like 48 hours to finish. 24. I don't know. I will tell you the exact details. When you get this assignment, you can ask me questions. Don't worry about it. You don't have to do it fully. You have to do it alone. Cameras, do it alone. But you can ask questions. I might say, I don't know, or give you a vague answer. But please, if you have a question, ask it. Yes, don't be a stranger. That's about it.
Ta-da.
That's
good luck in your exam period. Something with students.